Hello everyone. Today we are going to move away a little bit from the energy generation series and we are going to implement a simple quadcopter with automatic balance and hovering and all those things that you see in normal drones. So we are going to try to accomplish something like this. You can see the drone here. It's actually hovering right now. If I apply some throttle to it, it goes up and it kind of balances in place, maintains altitude, and then I can basically pitch and it will stop automatically in place. I can pitch forward, I can pitch backwards, and I can also roll to either side, and it will basically balance itself out while I'm not providing any input. Yeah, I haven't implemented yaw yet. That's going to be on part 2, but I will also show you how to basically right now I'm still using the third-person controller, and I'm just passing the input to the quadcopter, which is an actor and not really a pawn that can be controlled. If I set the quadcopter to pawn as the base class, it becomes controllable if I possess the character with it, and then you could see the first-person view from the drone perspective. I'll do that in the end. I haven't done it in this first try that I did, but I'll do it during this episode. So let's get started. Let's see. We stopped in the last tutorial with the generation of the solar panel based on the angle of incidence with the solar panels. I just removed, this is basically the same project, I just removed the traces, the line traces. The sun is now underneath us. So first thing I'm going to do, I am going to create a folder for this tutorial. Actually, I am going to create a folder for the tutorial 7. I don't think I did it last time, or maybe I did, but anyways, it's just an empty folder. We didn't do anything, we did everything on the other folders. Anyways, just for completion. And now I'm going to create tutorial 8. I'm going to call it Quadcopter. And in this, let's start by creating our physical quadcopter. I'm just going to get rid of these. Let's see, let's create a new blueprint. Let's make it an actor, and let's call it BP quadcopter. So this quadcopter is going to be kind of simple. I am just going to shamelessly copy from the other project that I still have open here. I'm going to create a couple of static meshes. Let's call this one arm1 mesh. This is going to be basically a 1 meter cube with some tweaking. Let's see. Feel free to use your own measurements for the body of the quadcopter. I'm just going to use some values that I used before and sounded kind of sensible. Let's see, let me just tweak the camera a little bit here. Yeah, so it's a bit slower. Let's just duplicate this guy, call it arm2 mesh. And arm2 is going to be -45 here, and the rest is going to be the same, so we just get a nice cross. And now we need, let's see, 4 cylinders for our for our motors. I'm just going to call it engine1 mesh, and this is going to be a cylinder. I Actually, I might need to include some things here. Is this what I want? Shape cylinder? I guess it will do. So let's just do some tweaking here. I want this in -11, -11. I want this to be 0.02, 0.02, 0.02. So we have a a nice little kind of engine in the end of the arm. Now let's duplicate this guy, call it engine to mesh, and engine to mesh is going to be on position 11, 11. And let's duplicate that again. Engine 3 mesh. Engine 3 is going to be -11, 11. And duplicate once again. Engine 4 mesh. And this is going to be 11 and -11. Cool. So now I could use a way to figure out where my quadcopter is facing. So I'm going to duplicate this and I'm going to call it body mesh. And it's still going to be a cylinder. It's just going to be in 0, 0, 0. And it's going to be 0.1, 0.05, 0.007. Okay, so now we have like a nice shape that we can use to figure out the direction of the quadcopter. As a root component, we need a box. I'm going to use a box collision. We could use something else, but I think a box will work. So I'll just make this the new root, and I will make a few changes to this. Namely, it's going to be 16 by 16 by 0.5. So we have a nice collision box for this guy. And now I am going to set it to simulate physics. I'm going to make the mass 1 kilogram, which is kind of a good weight for the quadcopter. And I'm going to make it block all dynamic, just so we are just so we can collide with stuff. Okay, so let's see, what else do I need? I might need some things here in terms of constraints as we develop this, but for now I think we are good. Let's see, another thing I need is the ability for this actor to receive player input, otherwise it's never gonna work. I'm going to put auto receive input player 0. I don't really care about replication and networking right now because I'm not doing anything with network, so I'm gonna leave all that stuff disabled. Let's see what else. Yeah, I think we're good. So now let's go to the event graph. I need to check if I should start with the component or okay, let's start with, I'm not going to need the begin overlap for now. There's a bunch of ways to do this in terms of how to apply forces to quadcopter. Basically, there's a bunch of ways to make altitude stabilization and you know, the quadcopter being able to react to the input that you give it and being able to be stable in the air. The way I chose to implement this is basically depending on the altitude that you want the quadcopter to be in. So I'm just going to tell it to always try to be at a certain altitude, and even the engines independently, I'm always going to tell them to try to be at that same altitude, which means in practice that the quadcopter will try to stabilize itself in a horizontal position always. No matter the pitch, no matter the roll, no matter the altitude, it's going to try to maintain that altitude across all 4 engines. And so in order to do this, I am going to create a variable called desired altitude. It's going to be a float. And the first thing I do when I start, when we start playing, is we store this desired altitude. So the whatever altitude we have the object in the world at, that is going to be the current altitude that we want to keep the quadcopter in. So we're going to get actor location, and I'm going to split this pin, and this desired altitude is basically the Z coordinate or the Z coordinate of the quadcopter. Cool. So now, first thing we need to do is we need to be able to apply some throttle to this. And the way I'm going to do this is I'm going to create a function called handle throttle. And this function is basically going to control your input for going up and going down. And it's going to need an input. It's going to take delta time, because we always need delta time to calculate the small amounts of force that we apply to anything, because basically a tick is just one frame render. And we don't want to apply a huge amount, just a tiny bit, just so the sum of it will amount to an X amount per second, if I make myself clear. I'm not sure. So this handle throttle is just going to set the desired altitude for us. So if I press one key, it increases the desired altitude. If I press another key, it reduces it, and then the motors will follow along. So we just need basically to edit the project settings and make sure we have this axis set up on the input. We're going to inputs and axis mappings. I am going to do one thing. I am going to change the existing mappings for the third-person controller to something else, because I want to use WASD for the controlling of the quadcopter, which means that I need to change, like this W, I'm going to change it to T. I'm just going to move all the inputs for the third-person character to the right of what they are now. So I'm going to make it TFGH. So I just need to change the move forward, the move right. A becomes F, and D becomes H. This way I can still control the third-person character. I just control the quadcopter on the main keys. So let's create a new axis. We're going to call it quad throttle, and it's going to have two key values. One is shift, left shift to go up, and left control to go down. So I need to put a -1 here. Cool. So what we're going to do in this handle throttle, we're just going to get quad throttle, the axis value of the throttle, and we're going to multiply that by delta time. So we get the, actually we can multiply it first by a throttle multiplier, but yeah, it's the same in the end. So I'm just going to keep it like this, because I did it like this on the other project. So I need another variable. I am going to call it manual throttle force multiplier. This might seem like a big name, and I should probably change it to I don't know, throttle power or something like that, but I had many iterations of this to get this working, and I probably created way too many variables. And this is the name I came up with. You can feel free to change it basically. And now I'm going to get the desired altitude, and I'm going to add this value that we just calculated to the desired altitude, and in the end I'm just going to set the desired altitude. Basically I'm incrementing or decrementing the desired altitude based on the input from the quad throttle. So that's the handle throttle. pretty simple. Now I have to do some altitude stabilization. And first we need to call this function, the handle throttle, and pass it the delta time, and that's all fine. Cool. So now let's create another function called altitude stabilization. And this function is also going to take a parameter called delta time. I want to pass in the delta time, and let's just put it here so I don't forget about it. And altitude stabilization, connect this. Actually, let's make this a little bit prettier. Make like a small hub that comes here and comes there. Yeah, that's neat. Cool. And what did I do? Unnamed parameter. What? Okay. Let me just delete that, compile, add it back. Okay, for some reason the name of the parameter hadn't been saved yet or something like that. Anywho, so cool. So what we need to do on the altitude stabilization, we are going to need a special kind of calculation called proportional integral derivative, which is kind of a linear interpolation, except much better to correct errors, and it also takes into account errors over time. So basically you give it the any current value that you have for a particular function, and you also tell it the value that you want to achieve, and it will make sure that it corrects itself either way, positive or negative, until it reaches that target value. And there are 3 parameters that are actually the PID that control how it approaches this desired value, and one of them allows you to tell it how strong you want this approximation to be. If you want it to try bigger numbers and try to reach the number as fast as possible with the possibility of overshooting. Then another parameter tells you how it can correct itself in a more smooth way and how you deal with oscillations and errors over time. So it's basically a very well-known way to implement altitude, to implement any kind of stabilization in drones. Most of them use this. If you look it up, PID settings is a very common thing. So I want to do this in a generic way because I want to be able to use this inside of an active component as well. So I'm just going to create what is it? Let's see, blueprints, a blueprint function library. I'm going to call this BPF PID, and this blueprint is just going to have one single function, and it's going to be called PID calculations. I know I'm going to need some local variables, so I'm just going to create them. I need the integral, I need the error prior, I need the error, and I need the derivative. Now, this function is also going to need some inputs, namely the current value that we have, that I was telling you about, then the desired value, what we want to achieve with successive recalculations of this function, then the p-value, the I-value, and these 3 are the parameters that control how smooth and how strong the function works. A bias, I'm going to leave the bias always 0, but it can be used. If you are interested in knowing more about this, Google Actually, I can show you the exact link. Robots for roboticists / PID control. This is a very good, very in-depth article about PID control, and for one, it explains the algorithm that we're going to implement here, and also explains what each kind of term does and how it affects the function, and then how to tune basically the P, I, and D parameters in order to get a good response out of the function. So feel free to Google that, and remember that the PID settings that I'm going to use can for sure be optimized, so feel free to do so. Okay, so first thing I'm going to do is I'm going to set the error prior. Oh wait, we're not done here. So I need the bias. I was telling you that the bias I'm probably not going to use, but it's also explained in the article there. Bias. So I need the delta time as well, and I need the integral value, and I need the error prior. Since this is a function, and these last two values, we need to store them outside the function, and we also want to modify them inside the function. I'm going to pass them by reference, which means that any changes we do inside the function will also go outside. And you're going to see that we need to hold on to these variables outside the function for each kind of PID calculation that we want to do. So first thing I'm going to do is I'm going to set the error prior. Set the error prior to whatever the error prior is. Then I'm going to set the integral as well. And the integral is going to be this guy. I'm already preparing the kind of I'm already preparing to make this a bit neater. So that's why I'm adding all these reroute nodes. Now I want to set the error. And the error, according to the algorithm, is basically the current value minus the desired value. So it's the difference between what we want to accomplish and what we have right now. I'm going to do float minus float. This is going to be the error, and this guy is going to be the current value minus the desired value. Let's just put these guys a little bit neater here, if we can. Okay, cool. So now I want to, let's see, I want to set the P integral. And for this guy, I need a bit more space. Let's see, this should be enough. And the P integral is going to be whatever we already had coming in from the function, right? Plus, plus okay. This is going to be the value, plus the current error multiplied by delta time. So we take the current error, just move this a little bit, I multiply it by delta time, and in the process try to make this a bit cleaner. Cool. So P error times delta time plus P integral, that's the new P integral. Cool. And now we need to set the P derivative, and this one is also going to be interesting. It's going to be basically the P error minus the P error prior, so whatever error we had in the previous iteration of the algorithm. There you go. And divided by delta time. So let's take delta time from here, make it a bit cleaner, like so, like so. Okay, cool. Just double check. Yes. Okay, so it's going to be these guys and this is going to be the derivative. So now we're almost ready to do our operation. We just need to do a couple of things. One is set float. Oh, sorry. What is it? By ref. Set by ref var. And we need to set the new value for our integral. So this is going to be the value that we're going to set, and you can see that the pin for the function is a little bit different, which means that whatever target we pass in here, it will actually modify it by reference and not just keep it inside the function. And the value that I want to pass in is the integral that it comes from the start of the function, like so. I should probably make this a bit neater, namely take these guys out of the way here, and that's much better. Cool. And now we need to do the same for the error. So I'm just going to copy paste this thing, and the error is going to be the new error prior. Basically, we're going to set it out. And we also need the error from here. Oh, this is going to be the error prior. The error prior is going to be the current error of this iteration. And I'm going to move it like so. See if we can make it a bit neater. Yeah, that looks a little bit better. And finally, we want to return. And our return is going to have an out force. You can call whatever you want to this. I just called it force, but in practice it's going to be whatever correction needs to be applied to attain the desired value based on the inputs that we have. And now we just need to figure out this out force. And this out force is going to be the sum of 4 values. The first value is going to be multiplication of, let's make this here. Yeah, that sounds good. Multiplication of the error by the p, or proportional variable. I'm going to clean up these lines in a little bit. The second one is going to be the multiplication of the integral by the I input variable. The third one is going to be the multiplication of the derivative by the D variable. And finally, the last value is going to be the bias. So I'm just going to do a plus, float plus float, add 2 pins to this. So I can do this plus this guy plus this guy plus the bias. And the bias, let's make it like this. And now let's try to make this a lot more beautiful, like so, and like so, and like so, and like so. Much better. And this is going to be our return value. So we're all done. It might look like a gigantic kind of thing, but it's basically following the algorithm that you can find on that page that I showed you. So if I didn't make any mistakes and this is working, we should be done with the blueprint function library. Now we need to go back to the altitude stabilization. So first thing we're going to do, we're going to calculate the PID values. And I'm just going to call that function that we just created. The values I'm going to add here, feel free to adjust them. I came up with these values, but they work for me, but they can probably work a lot better. So feel free to adjust them. The value that we want to attain is the desired altitude. And the value that we have currently is the actor location Z coordinate. So this is where we at this Z, and this is what we want to achieve, our desired altitude. And now I need two variables. So I need to store the integral and the error prior constantly between calculations. So I'm going to create them here. I'm going to call them altitude control integral, and another one called altitude control error prior. Cool. And I'm going to get these, and remember that these two are going to get set, or they're going to get passed by reference, which means that the function internally is going to change them whenever it runs. And I also need the delta time to be passed to the PID calculation. So hopefully with each iteration of these PID calculations, I will have a value by which I need to apply some force to the quadcopter to maintain its altitude, or to make its altitude exactly the same as the desired altitude. So one thing more I want here is another variable to control the force multiplier for altitude control. I will call it altitude stabilization force multiplier. And another gigantic name, doesn't really matter. Let's just compile and give it a value of 2000. Again, this value worked for me. Feel free to use whatever works for you. I'm going to multiply this by the value that comes out of the PID calculations. Because remember, this is not going to be a force that comes out of this, even though I call it force. It's going to be basically kind of the amount of altitude you would need to apply during this tick to reach that altitude. So I want to translate that into a force that I'm going to apply to the engines. That's why I have this kind of multiplier. And also I need to multiply this by -1 to reverse it, basically. To make sure that the force is applied in the correct direction. And this is basically what we have at the end of this spin, is going to be the value that we're going to apply to our engines. But we don't have any engines yet. We just have meshes of engines. So before I can continue this function, I will need to create a component, and I'm going to call it. I'm going to create a new blueprint class. It's going to be an actor component, and I'm going to call it engine component. And this is going to be the class responsible by pretty much everything about the applying forces to the quadcopter, basically. So I need to, let's see. First thing I want to do. Okay, let's go back to the quadcopter, and here in our components list, I am going to add under each of the meshes, I'm going to add one engine component. Okay. I have to think a little bit about. Okay, maybe not. So let's add engine component and duplicate it, and duplicate it. I'm going to add, oh, it's not a scene component, so I messed something up. I need to change the base class settings here. It cannot be an actor component. It actually needs to be a scene component, because I need to be able to attach it to the hierarchy and not really just to the actor. So now I can attach it. I will put one under each of the engines, and I will make, I think I need to make the, yeah, I need to make the positions 0, and I'm getting a strange scale here. Shouldn't, let's see. I don't think the scale is important, to be honest. Okay, I'll just leave it, but the location is for sure important, because I want each of them to inherit from the relative position of the parent, in this case the static mesh. So I want them to apply force at specific points. This is going to be important for pitch and roll later on. But I'm looking at my other project and this is not really correct, because it seems to be setting this guy. It seems to be setting it in the center of my seems to be setting it in the center of the quad and not on the engine. Oh, now it's correct. Okay, cool. Maybe some glitch, I don't know. So they are in the right position. They will apply force in the right position. I'm just going to change this back to 50-50-50. I don't think it's really matters, but anyways, let's keep it consistent. So now we have our engines. I'm just going to rename them to engine 1 and engine 2, engine 3, and so on. Cool. One thing to facilitate I want to do is actually create an array of engines. So I'm going to call engine array to a new variable, and I'm going to make it of type engine component instance or reference, and it's going to be an array. This way I can, you know, just iterate the array and do stuff with it without having to worry about passing each one independently, which means that on event graph, not really. Let's see, construction script. Yes. So let's go to the construction script and let's just add all these guys to the engine array. Let's do add. I'm not gonna bother with add unique because I'm only going to add them once on the construction script. And let's just be really lazy and make this as bad as we can. Yeah, good stuff. And we move these guys. This is going to be engine 2. And go up there. Engine 3. Oh, nope. Engine 3. And go up there. Engine 4. And go up there. So whenever we construct, we just add all our engines to the array, and this way we can easily apply forces to all of them and whatever else we want to do. So now that we have engines, we can go back to the altitude stabilization and we can just iterate our engine array. Let's do a for each loop here, and for each of the elements, so for each of the engines, we are going to, well, on completed we're going to do a return node. Doesn't do anything, it's just for completion. And now we want to add a force to our engine, to each of the engines. And for that, we need to go to the engine component, create a function called add force. And I will explain why I'm calling it add force and not apply force. Basically because I want to be able to add multiple forces during one tick that only get applied in the end of that tick for each component. This means we can have multiple sources of input, like adding throttle to go up, and also pitch at the same time, and the composition of these values is what's going to be translated into a force at the end of the tick for each engine. So I'm going to create a local variable called force per tick, and this variable is going to keep being added to per tick, and basically the sum of all of that is going to be applied as a force towards the end. So I need an input for this. I'm going to call it force. It's basically the force that we want to apply or add to the force of this engine. I'm just going to add and set force per tick. Oh no, set force per tick. And this basically just adds stuff, adds power to be applied to by the engine. So here I'm going to take the array element and I'm going to do add force. And what's the force I'm going to add? Whatever we calculated from the PID settings. So that's that for the altitude stabilization. Now we just need to do some work on the components. On the event graph, and one thing I want to do right off the bat is I want to get a reference to let's see, I want to get a reference to the physics body. I have to think about this. Yeah, I have to get a reference about to the physics body, basically the box collision that we have on the quadcopter, because we can only apply forces on the physics body, and this is the way we're going to do it. I just want to store kind of a shortcut to it. So I'm going to get owner, the owner of this component, which is going to be the quadcopter, and then I want to do get root component. And the root component, I know immediately it's going to be the box collision, but in any case I need to do a cast to primitive component. And if the cast works, which should, I want to just promote to a variable. I'm going to call it physics body. And there you go. So whenever we start playing, each engine will have the reference to the box collision, so we can apply forces to it. And now I'm going to create a function called apply forces, and I'm going to call it, oh sorry, not here, I'm going to not here as well. What? Okay, so that's the only thing I'm going to do on event tick. This is going to have an input called force, and no, sorry, an input called delta time, and that's the only thing I'm going to pass in. Cool. So inside of apply forces, we are going to do just a couple of real simple things, namely I need to multiply the force per tick did I just lose? Oh, I created the oh, I'm sorry, I created the local variable. That's not what I wanted at all. I wanted to create a normal variable, force per tick, and it's not going to allow me to do this. So I'm going to rename this guy to P, and now I can call this guy force per tick. And what I want here is a get and a set, and not this, not this. And I'm just reverting whatever I did. Sorry about that. And now I can get rid of the local variable, which means that on apply forces, I can multiply the delta time by the force per tick. So I know which tiny amount of force I need to apply during this frame. I am going to just because I know that I'm going to do something extra with the yaw later, I'm going to create a local variable called pforce per tick. And well, let's just call it pforce. Okay. And I'm going to set, and this is going to be the value that I need to apply to the engines for now. And now I want to, let's see. First thing I want to do is I want to call another function, but I need the force vector that I want to apply to this function. So I'm going to get the up vector of this engine. So no matter where the quadcopter is rotating to, this is going to be the vector that faces away from the engine, no matter the direction. And I'm going to multiply this by the p-force that we just calculated, vector times float, and this is the vector of force that I need to apply. So now I'm going to create another function called apply force, and this is going to apply one single force to the engine. And the apply force is going to take an input, and it's going to be called force amount. It's going to be a vector. And the only thing I'm going to do here is add force. No, I can't do it like this. I need to get a reference to the physics body. Then I can do a add force at location. And let's see. The force amount is going to be the force that I'm going to apply. I'm actually going to do this here so I can do another call to debug the force that is being applied to. The location is get world location of the engine. So this is where I want to apply the force, and that's the amount of the force that I want to apply. I'm just going to make the blueprint a little bit neater. I am going to create another function called debug force, or draw debug force. Draw debug force is going to take in the force location and the force amount. Let's go back to apply force, call the draw debug force, and this is going to be the location. Oh crap, I hate when this happens, when I don't compile and then the functions don't have the correct variable names in there. Okay, it's force location and the force amount is coming from here. This is just so we can visualize the force that is being applied. I will implement this in a second. So this is all we want to do. It's basically apply the force to the engine at the engine location, and yeah, basically based on the PID calculations, we're going to apply this. So now let's just really quick do the draw debug forces, which is just going to draw a debug line. So draw debug line, and it's just going to be the force location is going to be the line start, and the line end is going to be the force location plus the force amount. It's going to be the line end, and we're going to make it like bright green so we can see it really easily, and it's going to be there indefinitely. Cool. So I think if we try to run this, we should see something. We just need to add a quadcopter to the scene. So let's add one here. Let's make it in the air already, just so it immediately needs to try to start compensating and stay in the same place. Let's get it in front of our player, just so we see it. Just rotate this guy a little bit. Yeah, well, maybe not. We want to be able to see on the side. Okay, cool. So let's see what this does. And immediately it falls to the ground. And if I press Shift or Control, it does nothing. So clearly we're not doing something right. So even tick is applying the forces. The quadcopter is handle throttle and altitude stabilization, and it sets the desired altitude when we start playing. So let's see if we can debug this. Just taking a look at my project on the other side. Okay, one thing that might be wrong might be the multipliers. So manual throttle multiplier is 0, shouldn't be. Let's make it 150. Altitude stabilization force multiplier is 2000, which is correct. The altitude control integral and error prior should be both 0. Let's see if that affects in any way. No, not really. Okay. So we don't have any errors, which is good. We just don't have anything in terms of altitude stabilization. So let's see, we could debug what's coming out of this PID calculation. So current value, desired value. I could have made the mistake on the PID calculations function, that's for sure. It's a very big blueprint. So let's see, I'm going to print a string here just to try to see what kind of force is coming out of there. -20, and if I press shift, oh, I see it's increasing. So it could be just a matter of not having enough power. It is, however, negative, and I would expect it is increasing, so it is trying to correct itself. It just doesn't have enough power. So let's keep adding a little bit. I think it needs about 2000 to 3000 to start doing something, or maybe more. So maybe that's not the best way to try this. Let me double check the values that we have here. So 0.2 altitude stabilization 0.2, and then we are multiplying by the stabilization multiplier 2000, and we are multiplying by -1. Let's see. Let me try to print this value instead. So we do have a big value here. Yeah, and if I press it, okay. So I think it's mostly related probably to the application of the force on the engine component. Oh, I never finished this function. I'm so sorry. So apply forces. Yeah, we never finished this. So I need to, after we set the P force, we know the force to apply, force per tick times delta time. Now I need to apply force. So I'm just going to call the apply force function. And I need to apply the force that we calculated. And after I apply force, I no longer have any more force to apply. So I'm just going to set the force per tick to 0, just so we reset. So there's no forces anymore before the next tick. This is important because the PID calculations would continue to grow in power, and it would either keep raising or going down automatically. And that's not what we want. Okay, so we have some pitching issues here. I don't know why we shouldn't have, but we do have some, yeah, we do have some control, some altitude stabilization. I think we might have some problem here in terms of positioning of the engines maybe. So let me just double check that the positions are okay here. We have let's see, 00045, 00045. We have -1, -11, -11. This seems all fine. I just wonder if the scale of these guys is affecting in any way. Shouldn't. Yeah, let me just change these values to what I have here. 5, 2.5 and 0.35. I don't really think that's the problem, but in any case, it doesn't hurt. 5, 2.5, 0.35, 5, 2.5, 0.35. Okay. The quadcopter seems to be, it seems to be all correct. So it's either one of those PID calculations is not coming out with the same value, but it should, or there's another thing that I missed here somehow. That is strange. I don't get the same problem on my reference projects. So there is definitely something wrong here, which I'm not being able to discover just yet. I'm pretty sure it's related to the geometry or the physics body at least. Let me just lock the XY positions on the box collision. Yeah, there's definitely more power being applied to one of the engines. There's something really wrong here. I have to try to debug this by writing on each of the engine the power that is being applied. So add force at location. Location is the world location. Yeah, that's correct. Physics body, the force amount. Okay, I have no idea why this is happening, but let's see. We are applying force at location, drawing the debug force, and then I'm going to do draw debug string, and I want to see exactly how much power we are applying. So let's try to convert this to text and apply this at the position. See what we get here. It's really hard to debug like this. But it seems that we are applying everything correctly. Okay, since this is already becoming too long, I am going to stop here. I'll try to figure out what the problem is, and in part 2 we'll deal with pitch and roll, and maybe also yaw if I figure out the yaw in the meantime. So I hope you liked it. I hope you learned a little bit about PIDs and basically error control and kind of interpolation and altitude stabilization. And I'll see you next time. Have fun.